All right, this is day 26. We are talking more about hypothesis testing today. So we covered a little bit of this on Monday. We laid the groundwork for these ideas, but just to recap that a little bit, I want to talk a little bit about what we mean by hypothesis testing. The fundamental idea is that we're naturally skeptical. We have this baseline assumption that we're going to hold until we see sufficient evidence towards the contrary. Last time I used that coin flipping example, where we naturally assume that a quarter is a fair coin. There's a 50-50 chance that it comes up heads or tails, and it takes a fair amount of unusual activity for us to start to suspect that maybe it isn't actually fair. If we just flipped it twice and it came up heads both times, that's not really sufficient evidence. If we flipped it 100 or 1,000,000 times and it was kept coming up heads, then that might start indicating that something is different. That's the basic framework here. We have our baseline assumption, and until we see something that's sufficiently weird, sufficiently unlikely, we're going to hold that baseline assumption. Some other examples of this. Let's say that we have some new drug on the market, and our question is, does this drug actually do something? Is it actually better than a placebo? And if we test it on some sample and a few people do a little bit better, is that sufficient evidence that it was the drug, or was it maybe just due to some random chance? Many other examples follow this type of pattern where we're comparing population rates to sample rates. If the sample is sufficiently different than the population, maybe that's evidence that the sample isn't a representative sample of the population, that it wasn't just due to random chance, but that something actually is going on. For example, if we had a county where 20% of people are Hispanic, and we select a jury of a total of 100 jurors for the month, and only 9 of those 100 are Hispanic, then we might ask, all right, was this evidence of some sort of discrimination against Hispanic people in this jury selection process? Or was this maybe due to random chance? If instead there were 19 out of 100, I wouldn't be too surprised at that. Is 9 out of 100 sufficiently low? Well, we'll have to do some math to find out. I like the way the book structures this hypothesis testing. They make a point of making 4 distinct points, 4 distinct components towards doing a hypothesis test. And this is going to be true for all of the different types of hypothesis testing that we're doing down the road. We'll use the same format whether we're dealing with categorical or quantitative variables, and we will use the same formats for things in the future. So, big picture, the 4 components are stating the hypothesis. We want to state both the null and an alternate hypothesis. We want to write down what model we're using, as well as any assumptions that we're making in order to use said model. We want to do all of the calculations, and then we want to come to some sort of conclusion about our original hypothesis. We're typically going to either reject or fail to reject our null hypothesis. Okay, let's work through an example. I'm still in Halloween mode, so we're back to M&Ms and whether or not they're green. So the setup is that the M&M company, it claims that 30% of their M&Ms are green. They published their proportions, and this is what their published number is. So you buy a bag of M&Ms that happens to contain 140, and you count how many green ones there are. There are 37 green ones. 37 out of 140 is not 30%. So the question is this evidence that the published proportion is incorrect? That the manufacturer's claim that 30% of M&Ms are green is in fact wrong? So we'll answer this question with a hypothesis test and go through these steps just so we can see what all of this entails. So our first step is to state the hypothesis. Well, the null hypothesis is always going to be the status quo, the baseline assumption that nothing weird is going on. So in this case, our null hypothesis is going to be that this 30% number is correct. Okay. Well, this 30% is talking about the population's value. So the population proportion is 0.3. Our null hypothesis is always going to be about a population value. We don't really care what a particular sample has to say. What we really care about is the actual population value. So in this case, with categorical variables of color of M&M, we're talking about proportions. Later on, we'll do an example with quantitative variables where the parameter in question is the mean. But for this one, we're talking about what proportion of total M&Ms are green. Our baseline assumption is that the published information of 0.3 is in fact the correct number. For the alternate hypothesis, we have one extra step to go through, and that is to determine if we think this is a one-sided or two-sided hypothesis test. And this comes down to what the phrasing is for the question that we're asking. So here I have a normal distribution, which is representing what we would expect a typical sample of 140 M&Ms to look like. And as we've said before, this should be centered at 0.3. If 30% of M&Ms are green, then the expected value of the proportion of M&Ms that are green should be 0.3. It's certainly possible that out of a bag of 140 M&Ms, every single one of those was green. And that is possible, but extremely unlikely. That's going to be something way off here, or even something, more reasonable, like 70 of the 140 are green. So that would be an example of an event that is very notable. On the other side, if only, let's say, 10% of the 140 M&Ms were green, that would also be, pretty extreme. Both of those are examples where I would say that that sample is evidence that our 30% population number is in fact wrong. Well, any extreme value on the low end or on the high end would be evidence that it is wrong. So our alternate hypothesis is just that it's something else. It is either a bit smaller or greater than our original stated population value. So in this case, I would say that our null hypothesis is that the proportion is not equal to 0.3. Let's come at this question from another angle. Let's say that we came into this test with a preconceived notion that the M&M company wasn't giving out enough green M&Ms. Maybe we saw in the media some big accused scandal that they are not giving us enough green M&Ms. So instead of coming into this question asking if 30% is the wrong number, if we're instead asking, is the actual value less than 30%? Is the 30% too high? So I've got a preconceived notion that maybe it should be less than 30%. So rather than saying that my alternate hypothesis is that p is not equal to 0.3, my alternate hypothesis is that p is less than 0.3. So this is what we would call a one-sided alternative, because we are specifically interested in whether or not the M&M company's percentage of green M&Ms is less than what it's supposed to be. Back to the original question. Going back to the original question, if we are equally interested in deviations to both sides of the expected value, then we have what we would call a two-sided alternative, where our alternate hypothesis is that the population proportion is anything but the original hypothesized value. Okay, next component of doing a hypothesis test is to talk about what model we're using. So early on, there aren't a lot of models that we know. The two that we're talking about today are the one proportion z-tests, which is what this is. We're using this one because it is a categorical variable. If instead we had been using a quantitative variable, we would instead use the one sample t-test. Down the road, we'll have other types of models, so when we get there, it'll be very important that we keep these straight. But for now, we're just going to write down the generic name of the model and mostly just leave it at that. The other thing that we want to do in this component is to check our assumptions that the story, that the situation that we're applying this hypothesis test to, in this case the 1 proportion z-test, we want to make sure that the assumptions are met. So for this one, we have 3 conditions that we've all seen before. The first of which is the randomization condition. We want to make sure that the sample that we're talking about was a randomized sample from the population as a whole. So in this case, we're asking, all right, is it reasonable to assume that our bag of 140 M&Ms were M&Ms that were randomly selected from the M&M processing plant? And you could certainly argue that the way the mechanisms work in the M&M plant, that something weird is going on, but we don't really have any evidence for that. I think it is completely reasonable to assume that a given bag of M&Ms is a randomized representative sample of M&Ms in general. So I would say that this condition holds. Our next condition that we have to check is that the sample is less than 10% of the total population. Weird probability things can happen if this isn't the case, but for this M&M example, since 140 M&Ms is certainly less than 10% of the total number of M&Ms that are out there, which is billions, since 140 is less than 10% of that, we would say that our 10% condition is also met. All right, so then lastly for this one, we have the success-failure condition. That is that the expected number of successes, so NP, so the expected number of green M&Ms, needs to be at least 10, and also that the expected number of failures, so in this case NQ, the expected number of non-green M&Ms should be at least 10. Notice that this is different than the condition that the actual sample that we got had less than 10 successes or failures. What we only care about for the success-failure condition is whether or not the sample size is big enough so that the expected value, that NP, is at least 10. In our example here, 30% of 140 is more than 10, and 70% of 140 is also more than 10. Therefore, our success-failure condition is also met. Okay, on to the mechanics section. This is where we're going to be doing all of the actual calculations, and here our goal is to find this thing that we're going to call the p-value. Now, we use the letter P a lot in this class, so I just wanted to mention a few of those other instances just to keep it straight. This is something new. So we might say that the probability of an event occurring, the probability of A occurring, is capital P of A. We also use a lowercase p to talk about the population's proportion, and we use things like p hat to talk about a sample's proportion. So this p-value is a new concept. We're always going to write it as p-value, and it's different than these other instances where we use the letter p. What we're talking about here is we want to find the probability that something like our sample occurs just due to random chance. We're saying that assuming that our null hypothesis is true, in our M&Ms example, assuming that 30% of M&Ms actually are green, then what is the probability that the result we got from our sample or something weirder occurs? Okay, so we are assuming H naught. We are operating under the assumption that the actual population's proportion is 0.3. So in this case, this is a probability question. If 30% of M&Ms are green and we grab 140 M&Ms at random, then how many green M&Ms do we expect to get? Well, the expected value, or on average, the middle of this would be 0.3. We would expect 30% of that 140 to be green M&Ms. However, it's certainly reasonable that maybe 29 or 34% of M&Ms are in fact green. Right? Just due to the nature of how randomness works, if we grab 140 M&Ms, it's perfectly reasonable to get something a little bit different than 30% of them being green. And again, we're back to a probability question where what we're concerned with is what is the proportion of our sample, proportion of our 140 that is green. Well, the expected value on average should be 0.3, and this standard deviation of the sample proportion is given to us by p times q over n. Okay, so why is this a standard deviation and not a standard error? Remember, we use standard error when we don't know what the actual population's value is, and we're using information from our sample as a stand-in. So what we're doing for this part of the question is that we are assuming h naught. We are assuming that p equals 0.3, so we're pretending that we actually do know p. So rather than using the standard error, which uses p hat and q hat as substitutes, we're using what we believe to be the actual value for p and q. So if we plug in the numbers, we can see that the standard deviation of the various proportions that we expect to get in this 140 M&M sample, the standard deviation of this distribution is about 3.9%. So the proportions we expect to see is 30% being green with a standard deviation of almost 4%. So the value that we actually got when we took a sample of 140 and we actually got that 37 was green, well, that tells us that p hat, or the sample proportion that we actually got, is 37 out of 140, also known as a little bit over 26%. Okay, so on our normal distribution picture, the actual value that we got, this 26%, is, well, less than one standard deviation below the mean. All right, so big picture, this proportion, this 26%, is certainly less than 30%, but the question that we're asking is this substantially less? Is this enough different than our 30% original guess for us to think that some sort of shenanigans are going on and it isn't just due to random chance? Or do we think that this is a reasonably likely enough thing to just happen naturally, as in, is this just a coincidence? Or do we think something more serious, or do we think something different is happening with the population's value? So to answer that, we need to find the p-value. We need to know the probability that this thing occurs. Well, we don't want to know exactly the probability that this thing occurs. This particular outcome is actually fairly unlikely. Getting exactly 37 out of 140 M&Ms to be green is not very common. But what we really mean is, what's the probability that this outcome or an outcome more extreme happens? And because we said that this is a two-sided z-test, we're not only interested in the values or the situations that are less than something like this, we're also interested in situations where we get substantially more than the expected value by about the same amount. To find this, we convert our value to a z-score and then do a normal distribution calculation. So as always, the z-score is going to be equal to the value itself minus the mean over the standard deviation. In other words, it is the number of standard deviations above or below the mean our particular value is. So our z-score here is negative 0.92. What we want, or the p-value, is the probability that our random number is more extreme than negative 0.92. So less than negative 0.92 plus the scenario where it is bigger than positive 0.92. Or we could just say it's twice this number because this number and this number should actually end up being the same thing. All right, so since one of these is about 0.178, I used p-norm in RStudio to find this, then the total is going to end up being about 0.35. Let's call it 0.36. So this is the p-value. This is the answer that we're looking for this mechanics section. This p-value is the probability that we get an outcome at least as extreme as the outcome that we got here. 37 out of 140, or 26% of our 140 M&Ms being green, is on the low end, but something this notable, something this extreme happens 36% of the time. Okay, so the last step for this hypothesis test is to find the conclusion. Basically, this is to interpret what this p-value tells us about the question as a whole. If this p-value is a very small number, then maybe it wasn't just coincidence that we got the outcome that we did. Maybe our null hypothesis was wrong. If instead this is a big number, so I would say that 0.36 is certainly a big number for a p-value, then the fact that we only saw 37 out of 140 M&Ms isn't really anything to write home about. It's just sort of a fairly common occurrence. So the question is, where do we draw the line? How small of a p-value is small enough for us to reject the null hypothesis? It's a good procedure to, before we do any of this, decide what a reasonable cutoff p-value is for the given situation. A common convention is to use 0.05 as the cutoff. This is used in a lot of science papers. This is used for a lot of different studies. It somewhat has become the default cutoff p-value. That said, depending on what we're working with, it sometimes makes a lot more sense to use a stricter p-value of something like 0.01 or even 0.001 rather than 0.05. Our choice of cutoff p-value really depends on the context, how important it is that we don't throw out a null hypothesis that maybe we should have kept in the first place. Plenty more on what are called type 1 or type 2 errors either Friday or next week. But for now, let's just say that 0.05 is a reasonable cutoff to use. So since the p-value that we actually calculate is greater than this somewhat arbitrary cutoff, then we are going to fail to reject the null hypothesis. It's important to not say that we accept the null hypothesis. This is an innocent until proven guilty situation. The company is claiming that 30% of M&Ms are green, and this experiment, this 140 sample, doesn't do enough to dissuade us of that idea. By itself, it's certainly not evidence that 30% is right? It's, if anything, evidence that 26.4% is the more accurate number. But with a hypothesis test, all we are doing is either rejecting the null hypothesis or failing to reject. We are not confirming that 30% is in fact the correct number. Okay, so that's our first hypothesis test. It was a two-sided one proportion z-test. Two-sided because we were considering extreme examples in either direction, and a one proportion z-test because it is a categorical variable and we haven't talked about two proportion z-tests yet. But next time we will talk about one sample t-tests, which is the quantitative version of this, and then sometime next week we'll start throwing in multiple samples. But all the way through, we're going to use the same formats. We're going to state the hypotheses, as in the null and alternate hypothesis. We're going to state the model and check assumptions. We are going to have a mechanics section where we do all of the calculation to find a p-value. This p-value tells us how unlikely it is that we happen to get the scenario that we got. And then depending on that p-value, we will either reject or fail to reject the null hypothesis. Okay, plenty more about hypothesis testing next time.